Okay, hello to anyone out there checking out these lectures. This is a second lecture we're doing on optimal beta reduction. I'm Aaron Stump, and we're here at the University of Iowa with a bunch of friends here in the group. Chris and Tony, doctoral students, Ernesto, postdoc, and Colin, high schooler. And so today, last time I sort of introduced the idea of optimal beta reduction, and again, I'm not at all an expert on this topic. I'm giving these lectures to try to help improve my own knowledge of this, and so far it seems to be working rather slowly. We were joking beforehand, somebody had unplugged the AV when we got in here and had to plug it back in, and Chris was joking kind of, we'll stop at nothing to keep the secret of optimal beta reduction from getting out. It's kind of, well, the topic, personally, I'm finding it tricky enough that I don't really think you have to worry about the secret getting out too quickly. So anyway, what I want to do today is just do a bunch of examples, and we'll see I've got the whole set of graph rewriting rules, but it's important to emphasize this is the simplified version. You'll see as we look at the rules, there's one critical pair, meaning there's one choice of a term. You could rewrite it this way, or one graph. You could rewrite it one way, or you could rewrite it another. And the simplified version of these rules is non-deterministic. Just pick whichever way you want to go. But that's not adequate for doing this. I mean, you need some way to decide which choice to make. And that's what the full version of the algorithm does. There's several competing versions of this. Different researchers have proposed that try to resolve this one key point of non-determinism. So we'll see what that is. So we'll see the graph rewriting rules with this non-determinism, and then we'll see a bunch of examples. And that's all I want to do today. And then the next time, which won't be next week because we're going to do a practice talk next time, next slot that we have here. But in 2 weeks, which some people will be gone, so I don't know, maybe we'll wait a little longer to try to look at the actual one set of rules that actually does resolve the non-determinism. Okay, so without further chatter, oops, and the date is wrong. Sorry, it's not June 12th. It was going to be June 12th last week, but I couldn't figure out how to reduce one of the terms, so I canceled until today. Anyway, so here are the graph rewriting rules. Okay, so I guess actually we should recall what kind of graphs we're talking about. Well, I guess we'll see that as we look at the rules. Okay, so here, let's just start right off with the beta reduction rule. So if you're going to reduce a redox, and it's nice to highlight the links here. Oops, I can do it in blue. Oops. Oh, hang on a second. I think I've got a... Okay. Yeah, so... yeah, you can highlight the link that you're going to change. And so what happens is you've got an application. You've got this application right over here, and you're applying a lambda abstraction. And so what you do in this graph rewriting formalism, it's quite amazing. You just connect some things up, and here you see the wires. These links are labeled, and so you can see what this is saying to do is wherever A is going, connect that up to wherever C is going. So just sort of follow this path. This path right here gets turned into one connection, and then this one from B to D gets turned into another one. And so you just get these crisscrossing lines over here on the right. Really cool. Part of what makes this make sense is that it's presupposed that your lambda-bound variables are used only once. You say, wow, that sounds like a pretty bad restriction. How do I do something like lambda f, lambda x, f of x? You have to put explicit sharing nodes for this. So you write lambda, that's for the first lambda, another lambda, and then you've got an application node. Okay, that's fine. And you're applying 2 times the variable, the first variable f. So you have to put an explicit sharing node right in there. And then you've got and then you apply to x. And my graphs, unlike what I was seeing in some of the literature here, I'm writing my graphs with a lot of crossing lines because some people are sort of like tacitly flipping their nodes. And I'll talk more about this in a minute, which I find kind of confusing. So, you know, the first link out of a lambda is for the bound variable. The second link is for the body. So this link down here that I'm tracing right now, that's for the bound variable. And since f is used twice, we have to put this sharing node to merge those uses, basically. Okay. So anyway, so that's why it makes sense to just connect. You know, so over here back in the beta rule, you know, this link B here, that's for the bound variable. That's that link goes to the one and only one occurrence of the bound variable, and so that's why it makes sense to just connect that up to something else, because you're connecting to just one place rather than connecting to several places where you'd have, who knows, you'd have some kind of multi-graph or some kind of other structure if you were going to do that. Okay, so anyway, so that's the beta rule. I mean, hard not to just love that. That's just a constant time operation of gluing some links together, right? As opposed to carrying out a capture avoiding substitution, which is much more expensive operation and tricky to implement. Okay, now let's come to the next one. We talked about this one last time. Now suppose that you are sharing a lambda. So that's what we see on the left here. There's a sharing node above a lambda. Now how could that happen? Very easily, because, you know, over here I'm sharing an f. Now imagine I applied this thing, you know, just say imagine I took this thing and I applied it to some lambda, like just lambda yy, let's say. Right? So in that case, you'd have an application of this guy to, now what is identity function lambda abstraction in this formalism? It's pretty nice. It just looks like that. Because the one place you're using the bound variable is as the body. So you just have a link from the lambda node to itself. Okay, so if you beta reduce this, and we're going to do nothing but examples today, really, except reviewing these rules, so it doesn't hurt to get started right away with that. So if you reduce this, you're going to take, you know, so, and drawing this stuff then tends to get, you know, those lots of edges to sort of try to help show what's going on. Okay, so that lambda is going to move up here like this. Apply. We still are applying to the variable bound by that lambda, but now, and the sharing node stayed the same. That didn't change at all or anything. But now, right here, this link down here was the link that would have been marked, whatever it was, B, over in this picture. This link out of the top lambda is B. And so that link has to go to this identity lambda. So we get a picture that looks like that. Okay, so now you can see that here where we had this sharing node, now when we do a beta reduction, we're not just sort of pointing up to some binding site for a variable. We now have a sharing node over some, could be arbitrary graph, you know, for some lambda term. And so the next graph rewriting rule, which we saw last time, is for dealing with this situation. If you have a sharing node, a fan, let's see, this is a fan-in node. If you have a fan-in node over a lambda, you're going to propagate it and duplicate the lambda. And okay, and sorry, I forgot to put some labels on here for where these are going, but it's pretty clear what's happening. So, and this shows a really interesting point about this. This sharing node or fan-in or whatever we're going to call it it's also called the duplicator, because it's going to try to duplicate the graph it's below, or the graph it's above, sorry. It's going to try to duplicate that. Now, and the thing is, what makes this whole thing so subtle and tricky and pretty darn interesting is that you're going to try to do lazy duplication. You know, I mean, it's kind of known in this original Wadsworth graph sharing implementation of lambda calculus that Asperti and Guarini in this nice book that I mentioned last time that I'm still using as the reference, Optimal Implementation of Functional Programming Languages. They mentioned that, yeah, in that graph sharing algorithm, that there are places where you just have to copy a lambda term. You have to duplicate it. And in a sense, the improvement that's being made in this algorithm is to do the duplication lazily. And man, that it just leads to some tricky stuff.
Is that the only difference between?
The question was, is that lazy duplication the only difference between this algorithm, and there's several variants of this, and say just graph sort of pointer sharing, graph reduction? I think it would be fair to say that that is really the only difference, but it's the difference that then leads to a bunch of different changes. It's to implement lazy duplication correctly is where there's a lot of tricky stuff. But that's pretty much. And we were first starting to look at this after our friend Victor at Ethereum Foundation told us about this stuff. There's this guy Nadav, undergrad here, who did a final project on this. Basically, none of us realized that the point was to try to be lazy about the duplication. So we're seeing these algorithms and we're wondering, why the heck are people doing things these ways? It seems so strange. Why not just go ahead and copy things? You're yeah, sure, you can copy them, but the point is not to copy them unless you absolutely have to. And they say, well, if you're trying to avoid all this copying, so what justifies you duplicating a lambda? That's a good question. I guess the answer is, when you duplicate the lambda abstraction node itself, you can't possibly be duplicating any work. What you're worried about is duplicating redexes. And when you duplicate that lambda, you can't be duplicating any redexes. You're just duplicating the top of this term. So either this lambda, this duplicated lambda is going to participate in some beta reduction by being applied to something, or it's not. And if it's not, then copying this node isn't going to change anything. If it is, you have to do some copying anyway. So this is kicking off the first step of lazy copying, and it's doing it in the place that you can't run the risk of duplicating a redex by doing this. Yeah, question?
So we can see in that example, we're pushing the lambda abstraction up out of the sharing node. Is that because we want to bubble lambda abstractions to some top area so that we can eliminate any redexes that are important, I guess?
Yes, the question was, are we bubbling this lambda sort of through the duplicator because we want to expose the lambda for purposes of doing some beta reductions? Yeah, that's exactly right. And if you look at this very simple example, we can see that. Because right here, if we didn't have this rule that says you can bubble this lambda out, we'd be in normal form at this point. We don't have any applications of lambdas. But with that rule, now you'll take, you've got your lambda, and now we're going to bubble that lambda through the duplicator. So we're going to duplicate it. And if we go back and look at this rule again for a second, notice something very funny happens. I've got some commentary here to the side because some of these sources, as I said, are flipping. This topic of optimal beta reduction and these algorithms connect up with something that was independently devised by Yves Lafont, which was this idea of interaction nets and interaction combinators. And there, we just have it's a graph rewriting formalism where we have nodes that have a principal port and some auxiliary ports. And you think of these nodes, and so for example here, and it's all, let's see, so, well, okay, maybe I won't give the full little commentary on that, but the point is that these rules we're seeing are actually examples of interaction nets rules. And in that formalism, you think of these nodes. So here the nodes are lambda or this duplicator node as sort of lying in the plane. You can rotate them, but you can't flip them over. You cannot, spin them over. You can just rotate them around. And some of the rules in Asperti and Guarini are flipping these over. And it's actually confusing if you're thinking of these as interaction systems, which they, or interaction nets or whatever, which they absolutely are. So I don't really know why they chose to do that. But anyway, if you look at this rule, so you notice the one for lambda and duplicator, we duplicate the lambda, but we also add it was like we're duplicating the duplicator, and the reason is that so it's clear, this guy up here we're duplicating the bodies. I mean, we want to duplicate the bodies. The second links, this guy and this guy, are the links for the body of the lambda abstraction. So that's fine. We're sharing the bodies, or we're going to lazily duplicate the bodies. That's how you can think of it. But then why do we introduce this other duplicator over here? Well, remember, these are the binding. This here I'm marking in some other color, black. These are the links for the binding, for the variable, the actual bound variable. And so the effect of this rule is to say we're going to push this duplication, lazy duplication, into the body of the lambda abstraction, and the other side, this duplicator on the left, is essentially going to delimit where that duplication stops. So that's one way to say it. Another way to say it is that we're trying to share the body of the lambda abstraction, but we have different lambdas you start with. And so wherever that bound variable was, in one case, so here on link C over here, that was going to the sole occurrence of the bound variable. Now we've duplicated the bound variable. We have two bound variables now, and we merge them back together to reach that link. Okay, and so if you go and see, it's kind of, I think it's pretty nice to see how this is through an example. So if you go back to this example, so we've duplicated out these lambdas, so we're going to pass that duplicator down into the bodies, and so there in the body there's let's see, so what was there? There was, okay, we just had, this is identity lambda, so it's just a link going to itself. And so, but now that link that's over here, marked in red, that one is actually, there's now actually two links for that over here. So what the heck do we do with those? Well, that's where we join them up as well. So we do circle star, and that goes to the place where the bound variable was. And hey, it was right there. So we get this kind of thing. Okay. I don't know if anybody wants to ask anything about that. Okay, so that's pushing a duplicator across a lambda, and we're forced to. This was the part when I first finally understood what was going on here. It was like you're trying to share a part of a graph, remembering that there's some other parts, sort of incoming parts from different directions, match up with certain outgoing parts in different directions. So that's, C and D are both, D is sort of like the entry site into a graph, and C is the exit site. I mean, let's look at it over here. D is like where you enter some subgraph, and C is where you come out. You could think of it that way. And now we're saying, well, you can enter from several places, but depending which place you enter, it tells you sort of which place you come out. If you entered through the red door, you need to go out through the red door. If you entered through the black door, you need to go out through the black door. Okay. Let's see. And to make our example work, keep going on our example, I think I'll skip right to this third rule. We'll come back to this one about duplicating application. We'll get to that in a second. But let's just look at this one. If these duplicators meet, okay, now again, this is where the whole pain of this algorithm arises. If you have two duplicators meet, one of two things is happening. Either there's a lazy duplication that's finally done, because sort of the starting and ending markers of that duplication have met, and it's all done. That's great. When that happens, you just connect wires up like this. You just crisscross the wires. And this, in some of these, like in the Asperity Guarini book, which I otherwise love to death, they flip this bottom fan in, so they just drew 2 lines up and down. But I knew that was funny because in the interaction nets papers, Lafont talks about actually connecting straight up and straight down is weird, because that's where you're actually, here we're connecting circle to circle, star to star. And so if you maintain the orientation in the plane of these gates, that means you're going to cross at this point. Okay, anyway, so you can either do that. That's one thing that could be happening. A lazy duplication is done. Just connect these wires. The other thing that could be happening is you have 2 different lazy duplications that are crossing. It's like, isn't this like in the ocean? You can have waves that cross each other, right? My physics knowledge is horrible, I'm sorry. But crossing waves, right? And they just kind of both go through each other and carry on. That's the other thing that might be happening. And this is where you get this critical pair. 2 duplicators meet up here. You either just cross wires or you push the duplicators across each other. And you have this little graph where you have to, the only way I could keep this straight is sort of like, okay, from A down to D, I'm going circle, circle. Now, bearing in mind that I'm flipping the order of these, here if I go A down to D, yep, I'm going circle, circle. Okay, that's good. And similarly, like A down to C is circle, star. Now up here it should be star, circle. Because I have passed these over each other, so the order of these labels has changed, the circles and stars. Okay, so these are the 2 things you could, this is the tricky part of this is where the source of all the trickiness. Do you have a lazy duplication that's ending, or do you have 2 of them crossing each other like parallel, different waves crossing each other in the ocean? Now, in this case, in our example, it's the duplication is done. So this redex here, this guy, those we're going to do, and so basically what I'm saying is with the rules we're looking at here, nothing tells you which one to do. Nothing tells you which of these choices you should make. Should you end a lazy duplication, or should you pass 2 duplications over each other? And in the full version of the algorithm, which we won't look at this time, but we'd look at in a couple of weeks or whatever, there's mechanisms to resolve that for you. But here you can pick either one you want and try to resolve it yourself. So here we're going to pick that, yeah, the duplication is done. And so then you get at lambda. Now if you say, okay, the duplication's done, so you say, okay, that means circle is going to connect up to circle. Okay, so this red path is sort of the circle to circle path, and here's the blue one, which is the star to star one. And hey, look, I just get 2 identity lambdas back. All right, that's nice. You see, and it takes a little getting used to sort of trace these paths through, but if you follow the circle path dotted in red there, you just started lambda and come back to lambda. And same with the other lambda. So another way to say it is, well, the algorithm decided that right here, there's just no help for it. We're going to have to duplicate this lambda abstraction because we're trying to apply it, and it's used in 2 different places. That's the fundamental place where you've got to do some duplicating. But lazily duplicating this is a very easy thing to do, because there's really no opportunity to sort of preserve some shared redex. You just end up actually duplicating the lambda abstraction, and then we could continue on. But I think at that I probably won't continue that little example. Okay. Any questions about that? Okay. So then, oh yeah, go ahead.
So have you looked at what would happen if you chose the other one? Does it set everything up, or does it? What
would happen if you chose? That's a good question. What would happen if you did, in this case, incorrectly, really choose the other one? What would it do? I don't know.
I have a related question to that. So the non-determinism, it's not just, not algorithmic, potentially unsound. So if you choose the wrong path, would that?
Yeah. If you choose the wrong path, you potentially are not going to carry, the reductions you're doing will no longer correspond to the original reductions on the lambda term. So it's a critical piece of non-determinism. You can't just kind of like, oh, let's just go that way. So in this case, you know, if you want to get a feeling for these rules, I encourage you to give it a try and see what would happen if you did take a different route here and pass those over each other. But I think the answer is that should screw things up. You should not get in the end what you expect to get. I mean, here and by the way, here we should just notice that, you know, we actually did. This is actually pretty readably. So far, it's just, you know, lambda x, lambda yy applied to lambda yy applied to x. I mean, that's some of these, when you get these graphs that have sharing, these fan-ins and fan-outs and all this, it can be hard to see what lambda term they represent. But this one is easy. There's no sharing node, so. Okay, and there's one more reduction rule here in the simplified version of these graph rating rules, which is this one. This middle one about where you have a duplicator meeting an application. And there's several things to talk about this. So I think I want to draw a more sort of informal picture here. So say you've got an application node, okay? It's being used somewhere, there's some argument here, and there's some context, you know, that wants to use it. And say that you've got this, like, I wish I was a better artist. So you've got this sort of wave of like, okay, we're going to duplicate. Duplicate. Now, you could ask, notice that there's only, the situation we're talking about is that we are going to, this rule we're looking at is going to do a duplication here. Okay, so coming back over to this, we do take, you know, this application node, you can see, is duplicated. Now you could say, there's two things you could say. First of all, you know, why are we doing this? Second of all, how is it working to send duplication nodes up and down like this? And third of all, why is this the only one? What if I have a duplicator coming some other direction? Shouldn't I duplicate this? Okay, so and the answer is that if you've got sort of duplication coming up towards in the functional part of an application, you're going to have to, you know, that's where there could be some lambda that's going to appear there to be applied to the argument. You're going to need to push that duplication forward to see if there's a redex. You can't just defer it. So that's where you're going to, and what do you do at this point? You say, okay, we've got to duplicate that application. For the context, well, you know, we have to merge back in. Okay, so I guess I'll have to break down from how I'm writing these, you know. So we've done the duplication here, but we also have to sort of push the duplication wave towards the argument. Let's see, I'm drawing these circles still. You know, the argument is here, the context is here. And then the duplication wave, of course, looked like something here, and then let's see. So the point is, it's the way I'm thinking of it is like this duplicating wave, or this duplicator, it's moving this way, and it hits this application node, and it turns the corner down towards this argument, and it has to propagate up this way. So that's sort of what it's doing. So it says that there's three questions. So like, how is this happening? Why are we duplicating this application? Well, as I was trying to say, you know, you're basically expecting that you could have coming here some lambda abstractions. And you've just you've got to put a lambda right next to an application for a reduction to happen. If you didn't move this duplicator across the at, then you'd be just missing some beta redexes you're supposed to do. Okay. Now as for the third question, why don't we have a similar one that says, okay, what if you have, here's the context again, and here's the sort of functional part, and what if you have a duplication coming up this way? Why don't you want to propagate that one? You don't want to propagate that one because there's no need to. You won't create any redexes there's no redex that could be sort of hidden by this. Suppose there's some lambdas, marching their way up from the argument. Big deal. Beta reduction doesn't care what the argument looks like. It just cares what the functional part of the application, the applicand, looks like. So you don't need to. And if you don't need to, in optimal beta reduction, you shouldn't. You're not supposed to do it unless you absolutely have to. In fact, that's one little complaint I have about. There's a paper I found called Lambda Scope by, among others, Vincent Van Ostrom, who's a brilliant rewriting researcher. There they just say, they give all these reductions, including ones that aren't optimal. And it's sort of up to you to realize that some of them you shouldn't do. If you're not aware that optimality is sort of the main goal here, you might not understand that point. So their rules would say, sure, propagate that through there in general, because they give some family of rules. Actually, I wanted to show, they have, you can actually find this Lambda Scope thing on Hackage. I downloaded it, and it's on my installation here, it's maddeningly, it's like, oh, it's almost, we're just toying with brilliance here for actually understanding this, because they have a bunch of examples. Let's see, including omega, which was causing me a lot of problems last week. You can fire this thing up, but at least on my implementation, my installations here, it spins around, which is kind of annoying. And you can sort of get it. You can stop it spinning by hitting space, but then you seemingly can't really reorganize the graph at that point. If you click on, with a right click on one of these nodes, and I can't really be sure I'm not exactly sure what we're seeing here. I don't know what all this is. They have a slightly different version of this thing, this graph rewriting algorithm. But you can click on red nodes. Those are nodes that could reduce. And it's all looking kind of nice, except to sort of decipher what's going on. Like, could you please stop moving and let me put you in some orientation? I can tell, but it's like, okay. That's why I was like, this is like, oh my gosh, this could be the key to understanding this, but like, I can't use the dang tool. But it's really nice what they have. It just somehow it's not rendering very well on my screen. So hats off to the guys who did that, but could you somehow give a hint about how to control this better?
We must prevent the secret of optimal beta reductions at all costs, including bad UI.
Yeah. We'll stop at nothing to keep the secret of optimal beta reduction hidden for everyone else. Okay. Anyway, so yeah. Okay, so, and I had these comments as I was so confused about the fact that these nodes are getting flipped. I won't go through my confusion with you, but you can see that if you want. Okay, so those are the rules. There's basically, let's see, there's 5 graph rewriting rules, and it's actually quite brilliant that they're all sort of constant time operations. You just connect some wires. Just connect this to that, connect that to that. There's no like substitution or these kind of big primitives that you usually have in beta reduction. And this right here is the source of the problem that takes what was looking pretty nice and fairly intuitive and makes it a lot harder to, makes it more complicated, is resolving this non-determinism. Okay, so anyway, I thought I'd show you now a few examples that I worked out already by hand, unless anyone wants to ask anything. Okay, so here's, let's let delta be lambda xx applied to x, and let I be lambda xx. So what if you just apply the identity to itself? Okay, so you can see the redex link is highlighted, and it just means that I tried to indicate sort of graphically, like this edge that's coming out for the bound variable. Let's see, so what is happening here? Yeah, you connect that up with the argument. So this edge, which happens to be edge for the body as well, gets connected to the argument, and you just get one of the lambdas back. Okay. Yeah, I think the examples we were doing before were even easier for following this. What happens if you duplicate, if you apply the duplicator term to identity function? So this delta looks like lambda, and then we are applying x to x. So that means we need a sharing node here. We need a fan in node there. And so let's see. So what are you supposed to do? You take this link here for the bound variable, this lambda, and you connect it, as I drew in blue here, to the argument. And so then you get this. You're applying, and then you've got a fan-in node right there, a duplicator. And so you got to push that lambda through there, as we saw as an example a little while ago. So you push it through there, and yeah, we worked through this just a minute ago. It lazily tries to duplicate, a single wire, and so then that just does do the duplication, and then you just do more beta reduction, and you're done. Now, what about delta applied to delta, which we expect to be, it's a non-terminating term, of course. So what happens there? Well, we do this, first we do this link right over here, and so that means we're going to, this at is, sort of moving it up here. As you draw these, of course, you're sort of rearranging your graph to try to make it look a little nicer as you go. So that goes up there, and this link here is going to go to the, that's going to go over to the argument. And so that means you've got this application, this duplicator, which is, of course, this one. And then where the duplicator was pointing just to the bound variable, now it points to the argument term. So there, we've moved the argument term down here. Now again, it's time to push a lambda across one of these duplicators. So you push it up here. When you do that, we have this sort of obligation wherever the bound variable is being used. So at this point, we have to fork things because we're sort of saying I've got the start of two different lambdas, a big portion of shared body, and then I sort of fork back off to the two different bound variables. And so, this guy right here is the fan out. It's fanning out of the body to the different variables, bound variables. Now this is a very, this is a good example. So now we have a few redexes we could do, and I actually really frustrated myself by doing this outer one and just spinning, taking like 17 reduction steps, tediously drawing out these graphs and not understanding what the heck's going on. And so I saw that Asperity and Guarini actually had done this example, thank goodness. And so they said, let's do this one. And you say, now remember, this is where we have our critical pair. Should we make this disappear? No, in this case we shouldn't, because this guy down here is really associated with this one. It really is this case of two duplicators crossing each other. In this case, the bottom one is sort of like the duplicator delimiter crossing another duplicator. And so we have to do this crisscross thing like this. Okay? So you push them both over, you basically duplicate both duplicators. And now we're ready to do this link where, look, we have a duplicator up to an application. So we want to sort of make this round the corner. That's how I think of it, and propagate up. So this guy, actually, I was trying to draw in blue to kind of show where it's rounding the corner, and I'll put this one in blue also. So you can see we've moved this guy, has moved here and there. Okay. And we duplicated the application. You can see we have 2 of them now. Now what should we do? Now we have, again, 2 duplicators facing each other. Which ones are which? It's getting confusing? It is a little confusing. But actually, those... So this is where we need some real machinery to figure out, hey, which of these rules am I supposed to... Which part of the critical pair am I supposed to take here? But if you sort of keep in mind, like this bottom one's paired with the top one, then when you moved it here, that says that this guy... Sorry, I need a bigger... I had this problem in class, too. You need sort of a bigger pointer to be able to say, okay, so this guy is paired with this guy and with that guy. So when this guy over here meets this one or that one, those should disappear. I mean, we should not duplicate that's not 2 waves passing each other. That's lazy duplication ending. And lo and behold, that's exactly what we have. This guy's going to meet the top guy, and it's going to meet this guy. And so if I just did them one step at a time. So sure, that means over here, right at this point, now we're going to just connect some wires. Okay, so which wires do we connect? Ugh. Okay, this at was going to a star, and then another star, and then down to here. So that means the at should just go down to there directly. And up here, this at was going to a circle, and then another circle and a star. So that means that at should just go directly to that star. Okay, that's how we get to this graph down here. Now let's do this link. That's an easy one because, it's just, again, we're going to just merge wires. So circle to circle, star to star. It looks like this. So we go here and here. All my wires are crossed and everything. But if you just sort of shuffle your graph around, just imagine moving it into the plane and letting yourself, shift things past each other, then you get this, which is exactly what we started with. So after a bunch of steps, let's count them. 1, 2, 3, 4, 5, 6 steps. You get back to where you started from. Now, of those steps, how many are actually beta steps? There's 1 beta step over here, and that was it. There's just 1 beta step, and then there are these steps that shuffle these duplicators around. So that's how that works. And you can start to see, if you're just sort of presented with this graph, like say you're just given this graph, and so like, what do I do? You don't know. There's not enough information here to sort of tell what you're supposed to do. Should you pass these over each other, or should you make them disappear? Now you say, this is all very silly. I mean, this. I see there's a real problem, you might say, but this is easily resolved. You should just label these guys. You should just say, okay, here is label, let's say this is labeled A, and this is labeled B, and just match, your guys that are matching have the same label. Wouldn't that solve the problem? No. Surprisingly, that's not enough. And I don't have... Yeah, question.
Before you move
Oh, yeah, sure, before we move on. Okay.
So when you were... go up a little bit more.
Yeah.
When you were on this graph, this middle one,
Yeah.
and you said at first you chose the left one, you went down like 17 different,
Yeah.
or whatever. So
I chose, in this case, I did the top redex here, I did this guy up at the top.
Yeah.
And that's just, turns out not to be a great decision, because there's all this other crap that's happening down here, and this just kicks off more of the same.
So the one we're talking about, like optimal reduction, like the smallest number.
Oh, yeah.
Like what allows you to determine like which one you should pick?
Which one you should pick? That is a great question. And I read now a little more. Last time we talked, people were sort of saying, you claim it's optimal, but you also say you can just do any one. And no, there's actually 2 parts of it, apparently. I read further in the Sperti Guarini book, and they say there's 2 parts of it. There's avoiding repeating work, that's one part of it, and there's only doing the work that actually needs to be done to get to a final value. That's the second part of it. And so these rules make sure you never duplicate work, but you might do useless work unduplicatedly, and so you basically still need to use some strategy to avoid doing unnecessary work. So and you basically do you can basically just do call by name. I think is what
Okay.
they say works.
Are you saying that call by name on this graph will make you pick that?
Yeah, well, no, because again, the sort of here, of course, there is no normal form.
Oh, okay.
And so, optimal steps to the normal form kind of doesn't apply.
Yeah. But if you had an example where it was a terminating thing, then call by name.
Then you should do that outer one. Then call by name would say you would do that outer one.
Gotcha.
And it might just happen, though, that kicks off even more complicated overlapping lazy duplications. And so, as far as working out an example, it might, your eyes might be bursting out of your head a little bit with the intricacies of it. And that's kind of what was happening as I tried to grind through this. It's like, now I have more duplicators. Are they passing over the other ones? What's going on? But that, it's a sound implementation that correctly, resolves that nondeterminism. Doesn't care what order you would do them in. It will be sound. It will give you the right answer. And then you just need to use this strategy to avoid doing any reductions that don't need to be done for the normal form. So you just the usual sort of lazy reduction strategy.
So I'm trying to figure out because you said like call by name would be
yes,
good enough.
I think so. I mean, also reducing under lambdas. Sorry, so we should.
Okay.
Sometimes people mean call by name does not reduce under lambdas. Here, you're supposed to reduce like just leftmost outermost.
Okay, so for leftmost outermost, is that enough to avoid the useless intermediate steps, or is it not enough? Do you need additional rules with that, some combined?
I mean, you won't if you do leftmost outermost and this thing, you will. You won't get. You won't do any beta reductions that you don't need to do, and you won't duplicate any beta reductions.
But you might still do useless
steps that are
not beta
reductions. These other little steps where you propagate things around.
Yeah. So
possibly.
Okay. So you're saying there's like a.
I don't know. I don't think that would be useless. I mean, there isn't any separate set of rules that I'm aware of. It's just like these are the rules guaranteed not to duplicate work, and then you just need to apply them in something like leftmost outermost to make sure you don't do any unnecessary work. And then the other rules about propagating duplicators around and stuff like that, you might have to decide what you want to be a normal form. I mean, these rules will end up with some graphs that have duplicators in them, sort of representing the fact that a term, if say you have some term, you normalize it for a while, you get a normal form that's got these kind of duplicators and things in there. And I think I even have an example like this. Actually, I do have one more example like that. This is the last one I wanted to look at. The question of what lambda term this corresponds to, there's a little algorithm that's needed to take a normal form graph, and I mean, I would assume it's essentially pushing the duplicators through, but you don't actually have to do that and compute the full term. You can actually sort of walk the graph with the duplicators there to figure out, they call it readback, to figure out what lambda term you've actually got. But I don't see why I wonder if that would be the same as just saying, okay, all these lazy duplicators, just not make it, get to some normal form and make these lazy duplicators not be lazy and just push them all through the term and see if then you'd see what term you had. I haven't studied this enough to know whether that is equivalent to what they say to do. So there's other little things about where the duplicators are being pushed. I mean, it could be that, I mean, if you go back to these rules, it could be, like, for example, say that, say that B and C were just lambda-bound variables. And say that in that sense, in that particular case, there's not really a lot of point in pushing this across the application. It's a little bit wasteful. Because say you just had two lambda-bound variables going to B and C, and that was it. And then down in D, there's who knows what. But you're basically just applying two variables to something Like you don't really need, there's no redux that's going to get created by doing this. So in that sense, you wouldn't really need to do that step here. So I'm trying to address your point about kind of.
So are you talking about whether there are some of these like steps that don't correspond to like reducing something that are end up being like in some sense wasted?
Yeah, that's what Larry was asking about. He was saying is these steps that are basically the rules for carrying out the lazy duplication, is it possible that you'll sort of wastefully do some of those?
Is there like an optimal lazy duplication?
I don't know. There is a paper, well, I'll talk about that another time maybe. There's a paper that talks about the cost of duplication, and the cost of duplication can be very high, but that's basically because there's some example lambda terms typable even in simply typed lambda calculus that take a large number of steps to reduce, that when you put them into this formalism, there's a humongous amount of sharing. So there's only a few beta steps that end up being needed, but there's a ton of duplication steps that sort of correspond to the fact that you had a lot of reduction steps to do at the beginning. That's what they say. I haven't mined the depth of that paper, but okay. So let me just show you my last example, then I want to stop. And this was some example that looks a little contrived. I mean, but that's just because we don't have a, here in Cedille land, our eyes getting better and better at picking up, useful pure lambda terms. But I don't know what this corresponds to. This is an example from Lamping's paper. So lambda f, lambda x, and then you've got this term that duplicates its input function g, and you apply that to some little lambda abstraction over here that just applies f. I don't really know if it's important that we have it eta expanded f here or not. Okay, so we pick this link, we do a beta reduction. So just to look at the graph representation, because there's two uses of g, there's going to be a duplicator here. So we apply g to applying g again to x. Okay, so you reduce that link, and your lambdas are the same up here. You have now these, this application, of course, is this one. And this one is that one. And this duplicator is the duplicator there. And now we just had to put this trivial little lambda abstraction underneath there. Now I see why they didn't eta expand it, because they actually want, in this example, to propagate this through. So we have this link to reduce right there. We push that through, and we have to introduce this corresponding fan out. So here, the lambda abstraction isn't totally trivial. It's an application of the bound variable f way up here to what's bound by the lambda, this lambda, which is y up in my textual version. And so where the bound variable is used, so we fork our lambdas, and now the bound variable was being used on this second link of the application, and that's where you need the fan out. And my wires get crossed because I'm trying to, seems like my wires get crossed all the time, but here they get crossed to try to faithfully keep the orientation of this node. Okay, and then you've got beta reduction to do here. And so we do that, and I'm sorry, this picture got a little yucky. Let's see, so this link is going directly to that circle port here. So it goes right down there, and this other link was going into this application. Oops, sorry, wait a sec. No, now we have to connect this bound variable port to the argument. So the bound variable port is on the circle, so we have to take the circle and connect it to the argument. There it is. And then I sort of got a little running out of space over here. Now do this. Now you've got an add of a lambda. Sorry, it's cluttered in there. We're going to do that one. When you do that one, let's see. The body of the lambda is here. So whatever the incoming port was to this redex is going to go to the body of the lambda. And so that incoming port was from circle, so you're just going to go to where the body of lambda was, which was star. So you make this little circle star loop like that. And let's see, and the lambda's bound variable was the start port here. And so that needs to go to the argument. Oh, crap. Oh, the argument, which was this one right here. So bound variable goes to star. The argument goes up to here. Now star needs to go all the way up to there, and that's what it does. Star goes all the way up to there. And now you have something that represents church encoded 2. What did we start with here? It was something pretty much like that. Yeah, just take basically F and put it down here twice. But if you look at the graph we got, this is, and Lamping makes this point to, I was saying, naively, you would think you could just label your fan in and fan outs when you introduce them and just say, well, you only, to resolve this non-determinism, when matching ones meet, then they disappear, and when ones that don't match meet, they cross each other. Big deal. And part of the way toward explaining why that's inadequate is observing that these graphs can have cycles. So if you look at this, you say, okay, here we are, lambda, go down here, go through the circle port, okay, apply f, let's call it this first bound variable, to, now wait a sec, now we got to go out the circle port. If you come in on circle into some shared subgraph, so this part down here, this is the shared subgraph. We enter it up at this point and we exit it down at this point. So you entered on circle, you got to go out on circle. Ooh, and then we come right back to that very same subgraph again. And we have apply of f to, now we got to exit on the star port to over here. And apparently, but my grasp of this is not strong enough to be able to say more about why, when we have these cyclic graphs like this, we can get situations where just labeling matching fan in and fan outs is not going to do the job. You still can't resolve that's not adequate to correctly resolve the non-determinism. Okay, so that's all I wanted to talk about today. Basically, the rules. You can go back and look at them again, and we just did a bunch of examples with them. And if your eyes are melting a little bit from all the graph rewriting, just wait until we actually get the stuff that's necessary to resolve the non-determinism. There's beta. There's duplicating a lambda. Here's pushing duplication from the function part of an application across application. And then here's the tricky business. There's a lazy duplication starting and ending delimiter meeting, and so the duplication's done. Then we just match up wires here on the right. Or do we have two duplication waves crossing each other, and we have to do this? Okay, so in some period of time, might be several weeks now, because flock is coming up and some people will be gone for that, we will try to come back and look a little more at this. And I think that's it for today.